That could be this thing. It's been a while since so my name's Cameron, sorry, I should have my background. Your background? My background's mathematics and economics. So the master's in economics there. So yeah, it's one of those things where like stuff we talk about huge applications to I just got to think about
Okay, welcome back. So let's get started with the afternoon session with the second talk by Mike.
Thank you, Giovanni. Okay, so I'll pick up where I left off. For those of you that were here when I left off. This is another example of if you do something, give it a new name. Okay, so there'll be truth in advertising. Just to remind you, the two sort of coupled primary aims that I pinpointed this morning. One is scale up of dimension, and we're sticking with sort of conditionally linear, conditionally Gaussian time series models. And the other one is spending more time thinking about the models for the individual series. Okay, the customization. And this is all in the context of the sequential analysis, learning, and forecasting in state space models. The example will, again, one of the example here will be finance and portfolios. Okay, so this is really the first use of decouple, recouple, decouple to build and customize individual univariate models. Recouple, it's multivariate volatility. Portfolios are driven by the changes over time in the relationships between series. Okay. So truth in advertising. Some progenitors of these models, well, economists for several decades have talked about recursive systems. You build a series of univariate models and couple them together, sort of recursively. At one level, it's a special class, subclass of the models that I talked about this morning. The multi-regression term came out of Bayesian time series research community really back in the early 90s. And has some links to this, and they're really a special case as well. So there are at least two sort of other terms that you could use for the general way of thinking. And then I mentioned this morning in the example model I was using as the entree to this, the whole area of building models of covariance matrices by treating the Cholesky parameters, the Cholesky decomposition of those covariance matrices as primary. And that has a history too, going back, well, beyond 2005, but in macroeconomic modeling and forecasting, with time-varying vector order regressive models in particular. That's been a cornerstone idea. Okay, we're taking just this different view on it, and I'll reaffirm that and revisit that in the next few slides. Okay, so here's a way of thinking. So let's suppose your data is daily returns on a collection of stocks in the S&P, and you're interested in forecasting a few days ahead or a few months ahead, and you're doing portfolios. Okay, so you've got a set of decision goals. So this is Citibank, AT&T, eBay, etc., going down the list there, and I'll pretend I've got 400 of them. And T is day T, and we're standing at day T minus 1 with some information. So when I build customized models, I want to look at each series, and I'll start with Citibank, and ask the question about, well, what is my model going to be for Citibank? Okay. Whatever the model is, it'll be a conditionally Gaussian state space model. There'll be some idiosyncratic stuff in there, the plus epsilon, which will be conditionally normal, with some volatility. Okay? So I'll find some predictive information, and I'm calling it X. And that predicted information can include lag values of any of the series in the style of a sort of time-varying autoregressive model. And it can include other stuff that is specific to Citibank. Okay, so in the example here, I've got a couple of days lag on the Citibank price, some crosstalk from yesterday from a couple of the other stocks, in this case AT&T and Bank of America. And then I've got other things that I may want to use, other predictive information in the dynamic regression component for this particular stock. So customize the model and then go down the list and give it for each of them. So I'm building a set, the talk given by David Madsen this morning, he used the term dynamic regression, a set of dynamic regression models with other components. Each of them will have their idiosyncratic, and so what we have here in terms of the dynamic dependency network terminology is, if you like, an empirical network where the arrows all move from the past to the future. Okay? Now let's look at contemporaneous relationships. I sort of got into this a little bit today by posing the question, if I knew some of the outcomes tomorrow, which ones would I choose? Okay. So if I want to predict Citibank stock and I knew AT&T stock tomorrow, wouldn't that be useful information? I think it would. So let me choose a couple of the series and draw arrows up to Citibank for tomorrow. And in this case, just two. Let me go down the list and do the same thing. So I'll now go to AT&T, the second series, and do exactly the same thing. Choose some predictors tomorrow of Citibank's stock price tomorrow. I'm sorry, of AT&T stock price tomorrow. And in this case, I've chosen number 7, number 29, and number 131, whatever they are. And then I'll go down the list and continue that with a condition that when I'm in row J in my list going down these 400 stocks, the only contemporaneous predictors I can choose come from the list below. Okay? So the order here matters. I'm using some graph theory notation. PA stands for parents. So in this example, AT&T stock price tomorrow and Bank of America stock price tomorrow are parental predictors of Citibank. Okay? And the notation, the bold notation here, this is just a vector. In this case, when j equals 1, this is a 2 vector. When j equals 2, it's a 3 vector. Okay, I'm using that notation just to gather the contemporaneous parental predictors. Okay? And what this gives us, and this is intersection with graphical modeling, is a structure that begins to resemble some of the things I was talking about today of graphical models based on conditional independence graphs. And we'll see some of that in the next couple of slides. So that's the sort of basis of dynamic dependency networks. Index J for each of the series. The running example has 400 series. The first equation there is just the standard notation for a dynamic linear model, where there's a state vector for series J, that's theta JT. There's a set of known predictors for that series, that's the F. And then there's the residual, the nu t, one for each j, which will have some volatility structure. And the way we've constructed it from the cartoon is that we've built it out of two pieces. This F vector for series j has j-specific predictors in x, and then it has the parental predictors. So if you like, the what's known and lagged plus what is yet to be known in the parental predictors. And so the notation here has each of those having regression coefficients, which are time varying. And the partition form of the theta jt vector has these two subvectors catenated, just to build that simpler sort of standard representation of a dynamic regression for series J. If you want me to go through the details of the notation, you're going to ask any other questions, jump in. You have plenty of time. So as I say, then the X, generally Roman is known and to be known. and Greek is unknown. So the F vector is what is known or what is to be known. The parental predictors are not yet known because they're coming in tomorrow. Okay? And the state vector is partitioned accordingly. The final piece of the set of equations here, so it's a set of regressions, time-varying parameter regressions, is then assumptions about the residual term, dynamic linear model assumption that conditionally Gaussian. You can change that, but everything today is conditionally Gaussian. And they have volatilities, scalar volatilities lambda K, which are univariate volatilities on the precision scale. I'm going to gather those volatilities in a matrix here. This is the same notation as in my last example this morning, a diagonal volatility model for a set, the precisions of a set of conditionally normal random quantities. And they're going to be specific to each series, but they have implications across series because of the way the series are linked through their parental predictors. So let's go to the next slide.
Are these really just contemporaneously independent, or?
Yes. Yes. This has stopped working.
Yeah, I think the battery was not.
Oh, this is mine. This is mine. Oh, this one still works, does it? I've got a spare battery. Excuse me. I have a spare battery.
Always prepared.
Always prepared. Always prepared. I can't live without my. Oh, I've only got one spare battery. That's not good. That's not good news.
Brought the wrong kind of batteries.
Oh, I have two. Okay, ask Carl to ask a question if you want to. Got two batteries. Let's go just in case. Let's see. No, that's very strange, isn't it? All right, I hate to do this, but I'm going to have to stand here, unless somebody can get me a fresh one of these. He took the one from here away. We'll wait and see. This seems to have, it just seems to have stopped functioning. The fresh batteries. Oh, came back. Okay, same equations, nothing new. I'm just going to put it together in a vector matrix representation. Okay. Well, before I do that, this idea of this phrase recursive system, you can see we've got this sort of triangular array here, where series 1 can have parental predictors that are from the whole set of the others. Series 2 can't have series 1 as its parental predictors. As we go down the array, we've got a more and more restricted set to select from. That corresponds to the specification of a joint distribution for the set of y's at each time t. Everything's conditionally Gaussian as a product of conditional univariate normals. It's a compositional representation of the joint density of the set of 400 series on day t. Okay? What I have in here then, all of the state parameters are hidden in here. I haven't got them in the notation. The thetas and the gammas, sorry, the theta which comprises phi and gamma are hidden in here. I'm just highlighting the dependence on the data itself. Okay? So the specification of the model in this form is just breaking down a big multivariate normal, conditional normal, into a set of 400 conditional univariate normals. And it has this directed graphical structure because series below me in the order of the series can point to me, but I can't point to them. Okay? Your parents have to be older than you. They're higher in the list in terms of the index chain. Okay? And formally, it's a directed acyclic graphical specification of a particular multivariate normal distribution. Back to the terminology, multi-regression, Jim Smith and co-workers, Catriona Queen, back in the 90s, did some of this. They weren't involved in time-varying autoregressive component models and more of the extensions that dynamic dependence networks have. But they had the basic ideas back in the 90s. Okay, so we've got a set of what look like univariate decoupled models. They're coupled through these parental sets. So let's put them together in a big matrix, vector matrix form to understand what that coupling implies. First, let me take the linear regression for series J and give it a name. Okay, I'll just call it mu. So each series has its independent predictors and lagged predictors that have been customized to that series. I'll put mu in a vector, so everything's bold when it becomes a vector. I'll put the news in a vector, the idiosyncratic terms in a vector, that becomes the bold mu. So what's in the middle there, this gamma term, multiplying what? Multiplying tomorrow's yt. Yt is the subject of this equation. Okay? And now it's appeared on this side through this term for each j. Okay? So what is going on there is that we visit each series j, find out where the parental predictors are, okay, which indices they are in j plus 1 down to n, create an m vector full of zeros, and then in the locations for the parental predictors, we put the regression coefficient. So this gamma jt vector in our example for j equals 1 is a 2 vector. I've turned it into a row, and I've expanded it to a 400-dimensional vector by padding with zeros, except where those two non-zero elements are. So gamma here is a big sparse 400 by 400 sparse matrix. Diagonal, of course, is 0. Strictly upper triangular because of this hierarchical ordering of the parental choices. Okay? And you should keep this picture in mind, that it doesn't really look like this because these parental sets are going to be small. I don't want to choose 30 or 40 closing prices tomorrow to help me predict Citibank's closing price. I want to capture some market momentum. I want to capture some sector behavior. I want a couple of representative stocks and maybe an index. So these parental sets will be small. This matrix will be sparse. It's a choice you make. You have to choose the parental sets. Okay? So that's the picture to bear in mind. Then I mentioned, pointing to the screen down here, I mentioned earlier that what we have here is in economic parlance, in econometrics, it's called a structural representation of a set, a hierarchically ordered set of equations. Structural meaning that y is on both sides, and then if we do the calculations from this equation here, as I did this morning in an example in a different model class, we get a reduced form of that set of 400 equations, where the gamma matrix is, if you like, messing things up in both the terms that have gone into mu, the individual series-specific predictor terms, and the residual precision matrix. And just as this morning, the precision matrix of the residual is now a Cholesky style, where the idiosyncratic variances come in this diagonal matrix lambda, and this sparse matrix gamma is mixing things up. Okay? So that's just linear algebra. Let's go and look at these two pieces, the dynamic regression and the volatility matrix components on the next two slides. We'll do them in the reverse order. We already talked this morning about graphical structure, graphical model structure underlying a precision matrix. And this is what it looks like in a dynamic dependency network. Remember that with a Gaussian distribution, zeros in what we call omega t correspond to conditional independencies. We're starting with an equation that looks like this. Remember this blue-white image of gamma where the zeros, non-zeros are? Think about that, how that moves through this equation. I've just expanded that Cholesky quadratic form to give me my precision matrix. The first term, lambda, is diagonal. All of the off-diagonal is 0. The third term, well, lambda is just a diagonal matrix of positive numbers. So that just has zeros where gamma has zeros. corresponding to the parents of each series. Its transpose is a flip. It's a strict lower triangular matrix where the children point to the parents. Okay? So it has non-zeros. Well, the sum of these two terms here, or with the minus sign, has non-zeros between children, parental pairs. Okay? So in terms of a Gaussian graphical model structure that omega represents, children and parents are dependent. Okay? My child is conditionally dependent on me, whatever else you condition, and vice versa. Okay? And the final term, this quadratic term in gamma, well, you're taking row product with columns here. Okay? What that is doing is saying, find me the parents of common children. Find me those cases in which the parents are not parents of each other. In graphical modeling, that's called find me the immoralities in the graph if I don't recognize that. So if I've got two series, my example was AT&T is a parent of Citibank, Bank of America is a parent of Citibank. But if I have a model for AT&T in which Bank of America is not its parent, that's an immorality. So this term introduces a cross-product term, which in graphical modeling is called moralization of a graph. And that introduces additional edges into the precision matrix. When you go from gamma to omega, you get this pattern of zeros and non-zeros. Above the triangle, you fill in blue spots where gamma has blue spots, then you transpose it to get the below, but then you typically add more spots. Okay? For a higher dimensional problem, this is an example of 200 series. As long as this is sparse, this will typically be sparse. Okay? The more parents your series have, the more and more dense this precision matrix will become. If each series has got a lot of parents, okay, as you go down the list, those parents are going to all be tied up through this moralization idea. Question, Dave?
Can you help motivate why you might prefer this parameterization versus one where you mean centered by mean? That introduced again?
Yes. Modeling transparency and computation. You can do that, but it destroys all of the analytics. That's a good question. And we can come back to that later. Let me now look at the second component, the regression component, and how this parental construction modifies that. And this is related to David's question. David's question was, why didn't you subtract mu from YT before you built this model for the gammas, okay? And that would change things a little bit. But it would lose what is a practically important feature here that this slide is about. So I minus gamma is an invertible matrix. Powers of gamma get sparser and sparser. The nth power is 0 because it's strictly up a triangle in form. Okay, gamma squared has more zeros on the first super diagonal, and then so on and so forth as you take higher powers. So what's happening here then is when you multiply this mu vector by I minus gamma inverse, well, you're multiplying it by this. This picks up mu. Gamma picks up, to predict series 1, it picks up the mu for each of the parents of series 1 and multiplies them by the gamma coefficients on those parents. So if I use AT&T stock as a predictor of Citibank stock, I do my best then to predict AT&T stock tomorrow, and that has an implication feeding through to impact on the forecasting component for Citibank. Okay? With whatever weight comes from that row of gamma. So the mixing up of predictive components introduces an inheritance from their parents, modified by the gamma weights. And by the same token, gamma squared moves that out 1 degree, 1 step, and brings in a second order inheritance from grandparents. And as you go through the array, you know, how well you predict stock number 89, if it's a predictor of stock 71, which is a predictor of stock 15, which is a predictor of stock 2, then that predicted impact filters through these gamma coefficients. And as with the precision matrix, this is a map of non-zeros, zeros, blue and white respectively, of I minus gamma inverse from this example. The numbers matter, but the story is in the picture. And you can see some density built up. It depends wholly on the parental structure. But you can have several series having an impact through the piece that you use to predict them as you go up the hierarchy. So this is our triangular system of DLMs that comprises a class of dynamic dependency networks. Just restating the equations, a DLM for each series, broken up into two components, lagged and independent variables, contemporaneous relationships with their corresponding state vectors. And the way I've talked about it is the models are specified in parallel. We just did a discussion to look at the joint structure implies the theoretical recoupling. Okay? And we can think about now analyzing them in parallel and then using that theoretical recoupling to actually use them in prediction and whatever decisions those predictions feed in. To complete those models, they're not yet complete Bayesian state space models. We've got to specify how the state vectors, the theta jt vectors, change in time. And we've got to also specify how the individual volatilities, the lambda jt, for each of those univariate dynamic linear models vary in time. For the former, it's a standard conditionally linear Gaussian evolution equation. In the example I have today, this matrix can be ignored, it's the identity. Each of these state vectors is modeled as a random walk, allowing for variation, just the very standard first model you choose for anything, to understand if there's patterns of variation over time. Allow for them, don't predict direction, and see what data has to say. In many cases, the level of the degrees and relationships amongst what we call the innovation vectors, the omega jt are in this notation, in an evolution equation for a state parameter, would be structured. And in DDNMs, it's very natural to say that the parental state vector coefficients and the independent variable coefficients perhaps evolve independently. Just as an example, so in this case, this would be a WT matrix, which is block diagonal. A big part of the machinery of Bayesian state space modeling structures this component of a dynamic linear model by specifying the degree and relationships amongst the changes in state vectors through discount factors. Those of you that were at the tutorial yesterday with Giovanni will have seen some of that. They become parameters of the model, fixed parameters that we have to estimate. And I'll return to that in the example. So other than that, this is just writing down a very standard Bayesian dynamic linear model. The difference being this M of them. This has an index J for series J. Some of the analysis details. I made a point at the end of the first session this morning, an interest in maximally exploiting analytics. A conditionally linear, conditionally Gaussian model does some of the analytics it leads to. I mentioned the term Kalman filtering. The whole Bayesian machinery of one-step evolution, forecasting ahead at least one step, then updating when you see tomorrow's data. So that evolve, forecast, update step is closed form analytic. It relies on normal distributions for the states. Don't worry too much about the details and notation if you don't already know them. And gamma distributions for the precision parameter processes that are the univariate volatilities. So at each day in our data, at each day we can do that cycle of evolve, forecast, one step ahead, and then update, complete the cycle and move to the next day, independently in parallel across these series. Okay. You can do some of this looking ahead into the future for more than one step ahead forecasting. But because the parental predictors, the series up the chain, are values of the series down the chain, you have to think a little bit harder because you don't know them into the future. With some analytics, some nice recursions, the theory is very, very pretty. But to do it, if you want more than just means and variances for the series and covariances into the future, well, we don't do it, we use simulation. I said this morning I'm going to avoid doing Monte Carlo using Markov chain methods and sequential Monte Carlo and all kinds of other fancy things. I'm very happy to simulate exactly from distributions I can simulate exactly from. Cheap and easy to simulate from normal distributions. Cheap and easy to simulate from gamma distributions. So I use the term direct simulation. Okay? No fancy methodology. So let's think about how we do that. Let's suppose we're standing here at time t, day t, and I'll take k equals 1. I'm going to forecast the example. I'm forecasting 5 days ahead, so cap k is 5. Well, I start with forecasting 1 day ahead. So I go down to the bottom of the list of the series. I can't remember what let's suppose it was eBay. Suppose that was the last one. So little k is 1. dt is my information now on day t. I'm forecasting 1 step ahead to day t plus 1. I'm going to simulate from the distribution that the eBay model implies for tomorrow. I'll just take one Monte Carlo draw. Then I'll do it a million times. The eBay closing price tomorrow might be a parental predictor for number 399. Okay, let's suppose that's 3M. Okay? If it is, then I need to know tomorrow's price of eBay to forecast in the model for 3M. So I'll use that synthetic eBay price as the parental predictor in the 3M model. If it's not a predictor of 3M, it's not needed. But it is it will probably be a predictor of some other series up the chain. Then I'll simulate 3M and use it. Let's suppose we go to the next series, we go up the chain, and we find a series J, whatever it is, where 3M is actually a parental predictor. We need its value. So we'll just plug it in. And we'll recurse all the way to the top. You see why econometricians call this way of thinking recursive modeling, until we get back to Citibank. And that process will have generated, in reverse order, from m equals 400 down to 1, a vector that is a full draw from the exact multivariate normal, from the exact conditional predicted distribution in 400 dimensions for that multivariate time series. Okay?
Question? Are we assuming we already know the parameters, the value of the parameters?
So there are some parameters.
Yeah.
There, we'll get to that in a second. We are assuming that we know all of the parental predictor sets, which series are predictors of which series. So that's a lot of things to know. We are assuming we know, I mentioned discount factors. We are assuming in the model we'll have some AR lag parameter.
Yeah.
We're assuming we know that. And that's all we're assuming we know. That's enough to assume we know. We're assuming all of those fixed parameters. The calculations here, last slide, I alluded to the use of the standard Bayesian analytics for conditionally linear Gaussian models. So the state vectors, the theta jt vectors that comprise these two components for the parental and independent predictors, and the volatilities, the lambda j's, they have been integrated out in the computations mathematically. Okay? Moving ahead into the future, we actually have to then include the state vectors and volatilities in the simulation to move ahead from 1 step ahead to 2 steps ahead up to 5 days ahead. But because we've got a simple Markov model for the evolution of the states and the volatilities, that's true. So the same line of thinking goes to simulate not just the full vector from the full distribution tomorrow, But over the 5 days, this is 5 times 400, a 2,000 dimensional predictive distribution that we exactly see. And it's, you can see there's some exploitation here of partial parallelization. So if you're worried about it in going to 4,000 dimensions, it's straightforward. Okay, so as a summary, and then I'll come to an example. The decoupling is just to think about individual univariate series, but they're coupled inherently because of this hierarchical set of pairs. Okay? That, in anything other than a very small model, will typically want to be a fairly sparse set of relationships, as I indicated earlier. And by the way, as a side point, how you choose to specify those parents and how you choose to model the evolution over time of this gamma matrix, and I said we're just doing it with a simple random walk style model, leads to a whole new class of dynamic models, first-order models for stochastic processes on sparse, positive definite symmetric matrices. So there's some theoretical interest there, potentially for some of you. Simulation, direct simulation, forward simulation, trivial computationally, that exploits the recursive nature of the class of models is important for application. And I'll stress this again, this is a hierarchical system. Citibank is at the top, okay? eBay is at the bottom. So another choice that has been made is how to order these series, and that matters. You have a question?
Do you have to predict the x's ahead, just like you did the y's?
So, yes, and that's sort of taken care of in here. If I'm restricting, as the example does, to those x's including lag values of any of the y's. So for predicting Citibank tomorrow, I might have today and yesterday's Citibank price, and maybe yesterday's price of AT&T. As long as I've got lag values of the current or some of the other series in there, this way of thinking just goes through. Okay? There's no problem with that. So yes, moving more than one step ahead, if you've got autoregressive style predictors in X, in any of the X's, they need to be filled in as you move ahead with the predictions.
What if the x was like the price of oil or something?
That's a good question. So my example here today, I'm going to have, I think I've got 13 series, 12 series. And one of the things, the decision problem that we build that model for is interested in is a benchmark. It's a financial time series, okay? And so to do the comparisons properly, we need to be able to forecast the benchmark as well. So how do we do that?
Call it a y.
Call it a y, exactly. All right. So why do you ask the question? You can
No,
answer.
I'm sorry.
Just showing up. No, good. Very good question. So macroeconomics. So, you know, the Fed Reserve wants to publish predictions of GDP and wage growth and money supply. And they're all interrelated with, you know, another 150 macroeconomic variables that have to be predicted in order to build a dynamic economic system. So you have to extend the conversation. And ever more, then, you are going to need to be able to address scalability. So put it in the system. Okay, did everybody get the relevance of that? That's a really important point. Okay, so here's the example. So this is published in the Applied Statistical Modeling in Business and Economics Journal a few years ago. It has, there are 13 series. It's a little bit of an extension of a little cartoon example we had this morning, where there are some currencies and the oil price and the gold price and certain metrics, and there are two US stock indices in there. We've got the NASDAQ, that's series J equals 3, and the S&P 500. Okay, that's J equals 4. And the model is of log prices. If you want to do anything with short-term data in finance like this, don't look at returns, look at prices, and put momentum into the models. These are just two of the series. And we'll be looking at a 1-step and a 5-step ahead forecasting exercise with portfolios. Okay? And to the reply to the question a minute ago, let's look at the box here first. This is another series that will add to the mix. This is the CTA, Chicago Commodity Traders Index, that will add to the mix because we're interested here in gold and oil and the currencies in terms of their FX with respect to the dollar that may relate to those. You can buy that index. You can put that in your portfolio. Okay? It's a very low risk index. Can we beat it? So it's an interesting question to use series like that as benchmarks. The details of the analysis are not so important, apart from the fact that this was cruising through the recession here in terms of the test analysis. So models are fit and explored on half the data and then just run through purely as an exercise to understand and compare different models. Okay, to the earlier question. Which parameters are fixed? Well, let me tell you what the model is, and then we'll go down the list. Okay? So it's a very straightforward, very simple model, where each series has a local level. This is an intercept that is slowly varying. It has some lags of itself, which are series specific. So you might have 1 day, or 2 day, or 3 day, or 4 day lags, up to some maximum, on itself. And then a parental component where the parental predictors are drawn from those below. And of course the idiosyncratic. So here's the parameters. I'm going to use the term calligraphic M for model. Okay? So each series is customized. So it's an M sub J. And this is really just the set of things that I want to know in order to use the model. So I've got to choose the model order for the AR coefficients. I've got to choose its parents. Now this is not such a big problem. I've got 14 series. The CTA, the index, is the last one. So whatever the first series is, there are 13 possible parental predictors. For the next series, there are 12 possible parental predictors. Okay? So I can look at all possible sets of parental predictors. The numbers are small enough. There's a large number of them, but it's a few cycles. With 400 series, you can't do that. But with 12, you can do that. Then there are some other parameters. Discount factors to determine the level of variation over time in the state vectors series by series. So there are a set of fixed things that I don't know, but if I specify each of those, then I know MJ. So if I look at lots of combinations of them, this is an integer, this is a set of integers. This is 2 real numbers between 0 and 1, discretized over a range. So it's a discrete set, and you can look at all possible combinations. So now, I'm going to be a statistician and say, well, let's look at all of those possible models for each series and score them. And you can use whatever you want to score, statistical or decision. I'm going to be a statistician. I'm going to use standard statistical thinking, at least to begin. Okay? And what that says from a Bayesian point of view is if you believe reality is spanned by these models for each series J, then take some prior probabilities, we'll take them uniform, across those models, and calculate on each day t the posterior probability, and when you decide to stop, those probabilities provide the basis or part of the basis for comparing those models, for weighting them if you want to do Bayesian model averaging for forecasting, or for choosing them if you have a loss function and really want to choose a model or a subset of models. Okay, and that's nice because of the decoupled nature of these DDNN. We can do that for each series. And that's the guts of how you do that. In each series J, we run through time. On day t, we have yesterday's probability on each set of parameters for that series. Today, this is our forecast density from that particular set of parameters, conditional on the data up until yesterday, and knowing the values of the parental predictors and today's observation, that's just a number. It's a univariate t-density in our analysis. Okay? So recurse over time this equation from time 1 up to time whatever it is, 1,000 observations or whatever it is, to get a final probability across this set of models. And it's done independently because of the recursive nature of the structure of the DDNA. Okay? And that's really important because if you're listing the sizes of these models for series 1, we've got all possible parental sets and various values of the parameters and the model order. Let's suppose you've got 2,000 possibilities. And then you go to model 2, you've got slightly fewer. Suppose it's 1,900. Okay? It's getting smaller as you go down the train because the choice of parental sets gets more and more restricted. And because we've got decoupled analyses, the total number of combinations of possible models is the sum of 2,000, 1,900, 1,500, whatever it is. Whereas if you're building a 14-dimensional multivariate normal with a graphical model structure and everything else, as I alluded to this morning, it's the product of those numbers that would be the dimension of the model space you're working in. And you'd still be running the calculations today if you started them when we coined the phrase DDNA. Okay? So the exploitation of decoupling is not just thinking about individual models and allowing customization of the individual models, the MJs, but it's the computational benefit that accrues as well. Okay. So I'm a statistician, and I like to calculate statistical scores like marginal likelihoods, which convert to posterior model probabilities to compare, contrast, and sometimes to combine models. And here's a picture from an old teaching example of mine where there are just 6 models for one of the series. And I'm going through time, different data, and the 6 colors show you the relative probabilities on those models. Starting out with probability 1/6 to begin, after 70 or 80 observations, you see some volatility and some changes. And then you see one of the probabilities getting higher, the yellow probability, and a lot of the others getting smaller. And if you continue and have enough data, we know that what happens is that one of those probabilities will converge to 1. And the rest will converge to 0. Marco alluded to this in his talk this morning. He had 4 models, here we have 6. Okay? I'm a statistician, I'm a Bayesian, I play by the rules. Don't break the laws of probability. The laws of probability say if one of the models actually generated the data, okay, this is a good thing to do because eventually you'll find it. Okay? The laws of probability don't say do this, then average the models with respect to these probabilities when you know, when you know that the data was not generated by one of these models. And maybe outside the span of these models, whatever that means. Okay? You'll always converge, and you'll always converge to the wrong model. Okay? So it's a standard way of thinking about weighting and scoring models and understanding in an exploratory sense relative benefits. Some periods of time, some models do better than others, but eventually it degenerates. So in this paper, we did that. We did BMA because averaging several or many models together, if they're all a little bit different and based on different information, different parameters, is typically beneficial as long as there's not too many of them and too much redundancy. But we used a slight frill that's been around since the 1950s, and I'm giving you this partly as just to finish the story of think about goals and think about the pros and cons of using particular measures of structure for model comparison. And also because in recent years it's become very popular in time series and forecasting, particularly in macroeconomics. This looks like Bayes' theorem to take yesterday's probability over models to today's based on the conditional likelihood contribution of today's data. But there's a number in there that makes it not Bayes' theorem anymore. It's a forgetting factor, and this goes back to the late 1950s, early 1960s, in commercial forecasting systems in the UK, associated with the name of Jeff Harrison. And it's called a discount factor, but more recently, not so recently now, Adrian Raftery and his group rediscovered this and called it a forgetting factor. I like the term discount factor, and so do economists. This has become, well, this is old now, but it's de rigueur, and it's very routine in applications in Bayesian state space modeling in macroeconomics now. And all it's saying is before you update your weights on models, your posterior probabilities are not quite posterior probabilities in the usual sense anymore, you discount the effect of history a little bit. Okay? So if alpha's 0.99, you're saying I'm going to dampen down the set of probabilities from yesterday before I update by today's evidence. Okay? And this gives an exponential weighting, powers of this parameter alpha, on past data in contributing to these weights across models. If you're familiar with exponential smoothing or exponentially weighted moving averages, that's all it's doing. It's not formally part of probability theory. It's simply an intervention. The way I think about it, it's an intervention. It's a modeling device that we use because we don't believe that any one model actually generated the data. And it's a decision to act against the concentration of the posterior model probabilities. There has been some recent work on this middle point here of in the area of saying, well, look, we've got this set of models, this MJ, the series J. Let's have some kind of dynamics in the way those models are selected at each time point. This gets into sort of change point modeling and regime modeling. This is not that, but it's related to that way of thinking. And we'll come back to this discounting of model uncertainty, if you like, in the example. Alpha becomes a parameter. It becomes another choice. So let's look at the example. This is one of the series. You can't actually see the data on the top graph. It's the log of the oil price. And the graph just gets us back into the example. We're forecasting at each time point. We had training data up until here. And that training data was used to do this extensive search over all possible models for each of the series, using this power discounting idea on model probabilities. And at that point, we threw away some of them because they were of negligible interest, and we ran with a batch of models each day, forecasting 1 to 5 days ahead, then updating and then proceeding into the future. And over this period of time, a set of different utility functions we use to drive portfolios. Okay, and I'm just going to give summaries of one of those. So from a point of view of statistical understanding of what's going on, this is finishing up the story on the model selection, model comparison, model uncertainty point. What are the parameters? As we move through time, on each time point, on each t, we've got this full set of model probabilities. Okay, so we can look inside and say, well, look, in one dimension of MJ, I've got the AR model order. It's one of the parameters. That set of model probabilities then gives me a posterior distribution on each day for the autoregressive model order. On each day, we can do the same thing with parental sets for each series. And that's the question, what is the posterior probability on each day that 3M is a parental predictor of Citibank or any other series? Okay? Now here we've only got 14 series, so it's easier to digest. So just to give you some insights into a very natural phenomenon that you see in these recursive systems, these are the series in order. I dropped off the commodity benchmark. What we have here over time is a probability heat map. In the upper frame of the posterior mean of the AR model order for each series. And in the lower frame, the posterior probability that the AR model order is 2. Okay. So 2 days lag, some momentum effects. Let's start there. Let's look down the list. Let's go for the Swiss franc, the first series. Exchange rate with respect to the US dollar. As we look across the first row here, over all of the years in question, that's pretty much blue. So the probability is low. So the posterior probability that the model order is 2 is pretty low. As we come down the list, let's go down to Japanese yen. That's pretty high, 0.6, 0.7. Okay. The Swiss franc is the first listed series. So there are 12 possible parental predictors. And there's dependence amongst these data. Okay? So it's very natural to expect that the Swiss franc model, when brought to the data, will like to have a couple of parental predictors. As I go down the list, the Japanese yen is near the bottom. So you've got fewer choices of parental predictors. Okay? And therefore, it's very natural to expect that the series higher up will need some more action from the autoregressive component and maybe the volatility component. Okay. The sort of yellowy red band there is the S&P index. Okay. Well, these are FX. Well, oil and gold are down there. But pretty much the S&P is going to be weakly predicted by any combination of those guys. Okay. So it has a richer model, even though it's higher up in the order, in the listing, it has a richer autoregressive model. That's just a snapshot of how one way to think about looking at, over time, this question of model uncertainty. There's a little bit of the recession effect you can see in there when things change a little bit. And why don't we dig in and talk about interpretation. Same thing with the parental predictors. And I've just chosen a few of them. Let me pick out a couple of vignettes. So let me come down here. So this is the parental predictors of the Australian dollar fluctuations with respect to the US dollar. And the way they were ordered was the Australian dollar was right above the New Zealand dollar. And then the South African rand, and then the gold ETF, and so on and so forth. This is a probability scale that indicates that each day, what is at that time, based on the data up until that day, what is the posterior probability in this discounted analysis, that each of the rows indicated here was a parental predictor. And what you see with the New Zealand dollar is it's what? So if you're going to predict the Australian dollar with respect to the US dollar, and somebody could give you tomorrow's closing price of the New Zealand dollar, then buy it from them. Okay? A little bit of action in the South African rand, which is understandable from the point of view of what these currencies represent. Let me go up to the British pound, which is right above the Australian dollar in the list. Pre-recession, the Australian dollar was up there. It was a parental predictor with high probability that was useful for predicting fluctuations of the pound with respect to the dollar. Into the recession, bang, it's gone. Well, it's much reduced. It's not so clear. A lot of change points going on here over a period of time. Down here, in contrast, the Japanese yen is in there all the time. So the Japanese yen tomorrow is always a useful predictor of British pound tomorrow. So if you can buy it somehow or other, then please do. Okay. So one can get more into this. I want to come back to segue back into the decision analysis side of this, which is based on one particular choice of this discount parameter for model learning. And I want to sort of contrast the statistical and the decision analysis way of thinking about such choices. This is the same kind of picture as the two previous slides. Monitoring over time, day by day, based on data up until that point, based on mixing over all the possible models. the probability distribution on that day, the posterior distribution, for this alpha parameter with respect to a uniform prior way back at the beginning of the data. Okay. And what we have here is a grid of this parameter. So this is a number between 0 and 1. Okay. A lower value will discount history much more than a higher value. Standard BMA alpha equals 1. You don't discount history, you just accumulate information. Okay. And there's a grid of values here, you can't see them at the back. Alpha equals 1, 0.995, 0.99, 0.985, down to whatever it is, 0.95. And what you see in that picture is very rapidly, the posterior probability on alpha equals 1 drops down quite substantially. And on the other, whatever it is, I can't remember, maybe 15 values on this grid, the posterior probability is pretty stable, pretty much the same across that range. So from a purely statistical viewpoint, this is saying that pretty quickly the data model match is saying alpha should be less than 1. Okay, don't do straightforward, non-discounted learning because this data is pushing you into regions of model space. It's piling up probability on models that are then going to be denied by the data as you go through time. So allow things to adapt. And the second thing it's saying is it doesn't really matter what value you choose. Okay, some value in that range across that grid between, in this case, 0.95 and 0.995. Allow for some forgetting to that level. So that's one statistical metric for this particular parameter. Let's look at a couple of others. Let's look at blue mean squared error. So this is one step ahead. One step ahead forecast errors. So for each of the series, we just compute the one step ahead forecast mean. And then we're looking at raw forecast errors on the usual scale. Oh, I've got mean absolute deviation in there, so absolute forecast errors. Average across series and average across that time period. And the axis here is alpha, which starts at 1 here and goes down. It doesn't really matter what the numbers are on the score scales. It's the shape of the curves that are important. So they pretty much decay as you take alpha smaller and smaller. If we took alpha below here, they would eventually increase. Okay? Because the forecast errors would be whacking around because we're averaging over far too many values, far too many models with a very low value of alpha. We're discounting history radically. And you're basing preference for models and the forecasts based on them on very short, effective short time series. Let's look 5 days ahead. We're forecasting over 5 days, so this is looking 5 days ahead, very, very similar. Flattens out a bit more, but down to about, well, down to about 0.97, 0.98. It seems to be decaying. So this sort of suggests go down within this group of values. Go down to smaller values. Again, it would say beware, don't go down to alpha equals 0.5. So that's purely statistical metrics. Go back to the theme, one of the three themes here, and say, well, let's think about this from the point of view of the uses of the model and why it's interesting in the first place. What's the point of being able to more accurately forecast 5-day ahead fluctuations in these 13 assets as a purely intellectual exercise? Well, let's look at decisions that might use those forecasts. So a bit more information on the example portfolio. On each day, we're looking 1 day ahead and then 5 days ahead, 2 separate exercises. A particular utility function that penalizes risk of portfolios in terms of the predicted variation of the outcomes, and aims to make money. Okay, aims to make money in a couple of ways. It's nice to imagine that over on a 5-day period, we would target, say, a 1% return. Nice, 50% over here, or 0.5%. Okay, so build portfolios with constraints that push towards goals, real goals. The more you constrain the portfolio, the higher risk there'll be. So it's a balance between the two. Other part of this, and the other two parts of this, are the idea of a benchmark. So you can buy the benchmark almost for free. And if it's making money, why not? Well, let's ask the question, can you beat it? So rather than aiming to make 1%, maybe aim to make a minimum of 0.5% and beat the benchmark. Okay. That's another set of constraints. Then the third one is a very important constraint in management investment. It's to be decorrelated with benchmarks in expectation. Okay? So that if you know the benchmark is going down over the next few days, that's already built into your model because the benchmark is one of the series. You still expect your portfolios to be uncorrelated. Okay? So it's not going to pull you down in expectation. So there are certain classes of utility functions that are very standard, and there are different ways of building them. That's not really the main theme here, but it's useful background if you're interested in the details. So this is just looking at the 5-day ahead, the 1 day ahead. I didn't put in this, well, I've got the slide if you're interested, but the story's not really extended by it. A couple of metrics. This is cumulative return, just letting the models, the mixture of these many models run with the portfolio loss function over that period of test data. Cumulative percent return. This is the Sharpe ratio, which is good when it's high. It's a measure of return relative to risk. And this is a raw measure of risk, a standard deviation of predicted returns. So the blue, green, and red are 3 different versions of utility functions that lead to 3 different portfolios. And the blue one is the one that can make bigger returns, but it's always riskier. Okay, so it has higher risk, can make big returns, but it can bomb. So let's focus on the return graph. Again, this is with respect to alpha, this discount parameter. The data, statistics, says take it smaller, down to about 0.95. Worry about it going any lower than that. What this is showing is the red and the green portfolio make a better return than the benchmark. The black line is the benchmark. And then it sort of tails off as alpha gets lower. So as alpha gets lower, you're injecting more uncertainty in the analysis because you're discounting data more and more, throwing away more information. So there's more moving around, more noise in general. Sharpe ratio sort of peaks again at about alpha is 0.98. The 2 portfolios, red and green, are pretty much invariant to the choice of alpha. And the riskier portfolio is, of course, much higher risk. So on this basis, the next plot just says, well, if you've got to choose an example, choose about 0.98. Okay? Bit of a contrast with the root mean squared error and the MAD, which said, well, take a smaller value, maybe 0.95. Go lower if you want to, but worry about it. And the posterior probabilities that said take any of these values. We can't discriminate these values so long as they're less than 1. Okay? So the whole business of, if you like, tuning parameter selection is quite dependent on the loss. So at 0.98 for that discount factor, this just shows you that the 3 portfolios in the dark colors compared with the benchmark, which is the cyan color here, cumulative portfolios with a very blind running of the portfolios over the period of time. The benchmark, to be fair, cruises through the recession quite nicely. It's a very stable portfolio. But over the long haul, it's quite significantly dominated by mixing over models. The other graphs just compare the portfolios, and in view of time, I'll skip over those, and we can talk about that more in questions or afterwards for those that want to. So DENMs then, also known as recursive systems, also known as triangulated systems and univariate regressions. If you just take them and make everything sort of look like a dynamic linear model, a state space model in each of those equations, you can exploit the analytics. You can maximally exploit the ability then to decouple, to do forward filtering, forecasting and updating, modulo recouple across series when you're forecasting more than one step ahead, if you want to do it properly, but you can do that trivially by simulation. And very easy to implement. So that's pretty much for this session. I'll just raise this question. Already mentioned and alluded to earlier. Okay. Here we've got 14 series, the 13th series plus the benchmark. And I chose a particular order. Well, in some cases that's very natural. For example, a different context would be yield curves. So I've got the 10-year Treasury bond and any horizon between now and 10 down to 1 month. Okay, the Fed funds target rate. Very natural to build them in that order, you know, because of theory that says longer-term yields are based on expectations, and short-term yields empirically measure those expectations. Okay? In other cases, examples in other areas where, for example, in neuroscience with EEG, there are natural relationships amongst the series that you might anchor a choice of an order. With 14 series, you're not going to take all possible orderings of the series as a parameter. Okay, 14 factorial, and then within each of those orderings build models like this. It's not a parameter. Okay? But in certain areas, particularly with low dimensional series, it's very natural to think about an ordering. And that's really why it's kind of a common way of thinking in certain areas of economics. But in many cases, it's not. I have an example tomorrow with the S&P, 400 stocks from the S&P, where there's no inherent ordering. Stocks are companies and they're a structure, sector, industrial sector, for example, but there's no way of coherently thinking about choosing an ordering. And what you get when you choose an ordering, one ordering can be very different than choosing another ordering in terms of everything that's been described today. In terms of model structure uncertainty, in terms of forecasting accuracy. So the model order is an important choice and therefore a barrier if you want to go higher. Okay? The second question in the example, low dimension, we look at all possible parameter sets. Just a numerator. And you can do that with 14 series. Okay? It's a bit of computation. But going very much higher, that's not an option. So that whole question of how to think about, how to score, how to rationalize choices of parental sets opens up new R&D questions. And tomorrow, in the first session, we'll be coming back to more recent work that addresses basically both of these questions. Aiming to build on the ideas here, decouple, recouple idea that a recursive system inherently gives you with the benefits I've described, but aiming to get away from this fundamental feature of the dynamic dependency network framework. Okay, with that I'm done, and we'll be happy to chat and answer any questions or chat offline. So the paper I mentioned, the first listed paper at the bottom there, co-authors are Zoe and Amy. And it's not a main theme in this particular topic right now. Some of the examples and the ideas that I talked about this morning, the example with latent factor processes and so forth, were really a main driver of the thinking because they were one of the first, in terms of the Bayesian time series world, one of the first real recognitions of the utility of this sort of triangular system in a much broader way than has been previously recognized. And that partly responsible fellow is Josh Nash. Okay, with that, I'm done, and thanks for your attention.